Okay, so we're hearing so much about these new AI agents, right? They promise to automate everything, make life easier.
Yeah, the hype is definitely there.
But there's this nagging question, and I bet lots of folks are thinking it too. Can we actually trust them? I mean, seriously, could an AI just lie to us?
That's a huge one. Or even, could it somehow get into your bank account, your personal stuff?
Exactly. How do we know it's actually going to do what we ask it to? Especially if it's run around doing its own thing kind of independently. That's really what we want to dig into today.
Absolutely critical questions. And as these agents become, well, less sci-fi and more part of our actual lives, figuring out that trust piece is just paramount. We pulled together some really interesting sources to unpack this.
Yeah, we have. We've got articles looking at the basic challenges when you have like multiple AIs working together, these multi-agent systems.
Right. And then some pretty deep academic work on how those systems function when they're based on large language models, LLMs.
And we're also looking into this thing called the Model Context Protocol, MCP. There's some discussion around potential security issues there.
Uh-huh. Plus, we've got guidance from NIST, that's the National Institute of Standards and Technology, on something called zero trust architecture, which is basically a security mindset for situations where you just can't assume anything is safe.
Okay, interesting. And finally, a study that actually looks at all the ways these multi-agent AI systems can, well, mess up in the real world.
So yeah, it's a pretty broad look, isn't it? From the sort of theoretical challenges of AI teams to the really practical stuff, security, where things can go wrong.
So the mission today really is to pull out the key challenges, the risks we need to be thinking about, and maybe some potential solutions for making these AI agents trustworthy, especially when they're all interconnected and decentralized.
Let's do it.
Okay, maybe we should start with the basics. Multi-agent systems. What exactly are we talking about when we say multiple AI agents working together?
Right. So think of it not as one giant AI trying to do everything, but more like a team. A
Mm.
team of specialized AIs.
Okay.
Each one has its own particular skills, its own abilities, and they collaborate to achieve some bigger goal, like
Hmm.
putting together a project team.
Yeah,
You need different experts.
gotcha. So what are some examples?
Well, the sources mention things like simulating complex environments, maybe for training, or building virtual worlds, or even having AI characters do really detailed role-playing in games or simulations.
Mm.
And they're also being used for complex reasoning tasks.
Hmm.
Different agents can tackle different parts of a problem and then sort of pool their findings.
That does sound potentially way more powerful than just a single AI.
Hmm.
But having all those agents interacting, doesn't that create like a whole new layer of complexity, a new can of worms?
Oh, absolutely. That's a key point in the sources. The
Yeah.
complexity of managing those interactions just explodes as you add more agents.
Right.
You have to coordinate their actions, figure out how to resolve conflicts if their individual aims aren't perfectly aligned, make sure the whole thing stays coherent. It's much harder than with just one AI.
Yeah, I can imagine. It's like herding cats, maybe. Or conducting an orchestra, perhaps, is a better analogy.
Conducting an orchestra is a good one, yeah. You need to know what each part is doing and how they fit together.
So, how do you orchestrate that? How do you get this AI team to work together effectively?
Well, the academic paper on these LLM-based systems talks about global planning. Basically, first, you map out the whole job, the big picture workflow.
Yeah.
Then you break that down into smaller chunks, subtasks, and you assign those subtasks to the agents that are best suited for them based on their skills.
Right. Matching skills to tasks makes sense.
And then each individual agent takes its subtask and does what's called task decomposition, breaking it down even further into the specific steps it needs to take.
Oh, okay. So layers of planning.
Exactly. And the absolutely crucial part is making sure it all aligns. Every agent's little piece has to contribute consistently to the overall goal, like a project manager keeping everyone focused on the final deliverable.
Okay, that structure makes sense, but what about memory and
Huh.
communication? If they're collaborating, they need to remember stuff, right? And talk to each other.
Precisely. Memory and communication are vital. The sources really stress this. We're talking about long-term memory, maybe storing past work or learnings in external databases,
Hmm.
and also accessing broader knowledge, perhaps using techniques like RAG, retrieval augmented generation.
Or RAG, right? That's where the AI can look stuff up in external documents.
Exactly. It's like giving the agents access to a massive up-to-date library. So they don't just rely on what they were trained on, they can fetch current info, specific context.
Okay, so that helps them stay aligned and maybe learn over time.
Yeah, it allows them to keep track of context across conversations, share common sense knowledge, and even learn from how previous workflows went improving their teamwork.
Okay, so we have these collaborating, remembering AI teams, but some sources mention they can also be decentralized. What kind of extra challenges does that bring?
Ah, decentralization. Yeah, that adds another big layer, especially around scalability. How does the system grow and handle more work efficiently?
Right, if there's no central control.
Exactly. Resource allocation becomes tricky. How do you distribute computing power, access to data, efficiently across potentially thousands or millions of agents?
That sounds hard.
Yeah. One article gives the example of SETI at home. Remember that. Millions of home computers acting as agents, crunching data for signs of extraterrestrial life.
Whoa, yeah. Wow, that's a massive distributed system.
It is. And that system had to figure out how to distribute tiny pieces of work to all those volunteers without overwhelming anyone, making sure the processing was efficient. It's like managing a global network of researchers.
So how do you manage resources in something that huge and decentralized?
Well, you need clever techniques. Things like dynamic load balancing, constantly adjusting who gets what work based on their current capacity.
Okay, shifting work around automatically.
Uh-huh. And decentralized decision-making helps too. Agents can manage some of their own resources and tasks within certain boundaries, reducing bottlenecks.
So less central command and control.
Right. But what becomes absolutely essential, as one article points out, is standardized communication protocols. If these agents are all over the place, they have to speak the same language, follow the same rules for sharing info. Otherwise, it's chaos.
Okay, this is getting incredibly complex, and I keep coming back to this. With all this decentralization, agents everywhere, the security and privacy risks must just go through the roof, right?
Absolutely. That's a huge emphasis in several sources. Security and privacy aren't just nice-to-haves. They're fundamental requirements, especially in these decentralized setups.
Why especially decentralized?
Because without a central authority watching over everything, the system can be more vulnerable. Think data breaches, people getting unauthorized access, maybe even man-in-the-middle attacks, where someone intercepts communication between agents.
Yikes. Okay.
It's like trying to secure a city with no police headquarters, just lots of independent neighborhoods trying to protect themselves.
That sounds pretty dicey. So how do you even start securing something like that?
It has to be multi-layered.
Yeah.
You absolutely need things like end-to-end encryption, so data is protected when it's moving and when it's stored.
Right.
And strong authentication, making really sure each agent is who it says it is, so only authorized ones can access sensitive stuff or do critical actions.
And what about privacy? If these agents are sharing data?
Big concern. As they collect and share info, the risk of exposing personal or confidential data is significant. So people are looking at privacy-preserving techniques, like differential privacy.
I've heard of that. It adds noise to the data.
Kind of, yeah. It adds carefully calculated statistical noise so you can still do useful analysis on the whole data set, but it protects the details of any single individual record.
Interesting.
Ultimately, the goal is to engineer these systems to be inherently trustworthy and secure from the ground up. It's a massive challenge.
Okay, let's shift a bit. The sources also talk about assigning tasks and how things can go wrong if the system just misunderstands what's needed. Task allocation and misalignment.
Right. So efficient task allocation is about getting the right job to the right agent, the one with the best skills for it. Like in a warehouse, you want the fast robots fetching things, the careful ones packing.
Makes sense. How do they do that?
One method mentioned is auction-based allocation. A task comes up, and agents can sort of bid on it based on their abilities and how busy they are. The best bid wins the task.
Okay, like a little internal marketplace for tasks. Clever, but where does the misalignment risk come in? How does it misunderstand the user?
Misalignment happens when the system thinks it understands the request, but has actually interpreted it wrong. There's a great example in that paper analyzing failures using a system called ChatDev.
Okay.
A user asked it to make a two-player chess game. Specifically, they asked for standard algebraic chess notation for moves, like E4 or NF3.
Yeah, standard chess notation.
But the system built a game that used coordinate inputs instead, like move from by 1, y1 cube, by 2, y2.
Ah, so it made a chess game, but not the one the user actually asked for in terms of how you interact with it.
Exactly. And
Yeah.
that seems small, but it highlights a core trust issue, right? If it can't get a relatively simple instruction like that right, how can we trust it with something really complex or sensitive?
That's a really good point. Are there other common ways these systems mess up due to bad specs or design flaws?
Oh, yes. The failure analysis paper found quite a few recurring problems in that category. Things like agents just ignoring the specific role they were assigned.
Okay, going rogue, basically.
Or getting stuck in loops, just repeating the same action over and over without making progress. Or even losing track of the conversation history, which obviously just destroys collaboration.
Forgetting what was just discussed. Yeah, that wouldn't work.
It's like a team where someone ignores their job, someone else just spins their wheels, and nobody remembers the plan.
This feels like it leads us nicely into the Model Context Protocol, the MCP. The idea seems to be about connecting AI tools, but there are these security worries popping up. What's the basic idea of MCP and what are the concerns?
Right, so MCP, as it's described in some online discussions, is basically an attempt to create an open standard, a way for AI agents to securely connect and swap info with different data sources and other specialized AI tools.
Okay, like a universal adapter for AI.
Sort of, yeah. The goal is to make it easier to build an ecosystem where different AI capabilities can plug into each other. They even mention MCP registries, like directories of available tools and data. It sounds promising for making AI more powerful and interconnected.
It does sound useful. So, where did the security worries come in? What's the potential problem?
Well, that Hacker News discussion really flags a major vulnerability they called tool poisoning.
Tool poisoning. Okay.
Picture this. An AI agent has legitimate access to a couple of tools. Maybe one gets weather forecasts, another can access your email, standard stuff.
Mm-hmm.
Now, a bad actor creates a malicious weather tool that looks normal, but when the AI uses it, this poison tool subtly tricks the AI into using the email tool in a bad way, maybe forwarding your email secretly to the attacker.
Whoa. Okay, so the AI itself isn't bad, but it gets tricked into misusing its own legitimate permissions.
Exactly. It's like a trusted employee being manipulated by an outsider into giving away company secrets. The AI is the confused deputy.
That's genuinely disturbing. How is that even possible? What's the core weakness that allows an AI to be tricked like that?
Well, a fundamental problem seems to be that many current LLMs treat pretty much all input the same way. There isn't a built-in, reliable way for the AI to tell the difference between instructions from the user and data or responses coming back from these external tools.
Okay. So it can't distinguish user command from data from tool X.
That's what the discussion suggests. One commenter really emphasized this, saying, it's a critical flaw if we're going to let LLMs control important actions or sensitive data. The LLM needs to robustly know where information came from and what its purpose is.
So it needs to know definitively this is a command I should obey versus this is just information I received.
Precisely. The whole data is code idea comes up here. If an AI with access to powerful tools interacts with untrusted external data, that data itself might be interpreted by the LLM as a command.
Right, leading to unintended actions.
Yeah, like reading private messages, browsing the web in ways you never authorized, all triggered by malicious data disguised as normal input from a tool.
And that connects to the confused deputy attack you mentioned.
Exactly. The AI has permission to access, say, your email, the resource. The malicious tool tricks the AI, the deputy, into using that permission for the benefit of the attacker, the unauthorized entity. It's a classic security problem just applied in this new AI context.
And it sounds like just keeping track of what these agents are doing via MCP might be hard too. Lack of auditing.
That's another key concern raised in that discussion, yeah. Some commenters noted that many MCP implementations apparently lack good built-in auditing or metrics.
So you can't easily see what data was accessed by which tool when?
Pretty much. It makes it incredibly difficult to monitor for suspicious activity or even just debug problems. You're kind of flying blind trying to manage this complex web of interactions without proper logs or monitoring.
Okay.
And fundamentally, as that discussion highlights, securing a decentralized system where different services interact but don't necessarily trust each other is just a really hard problem. We've seen similar challenges in web security for years.
This paints a pretty worrying picture of potential holes in these interconnected AI systems. Is there a better security model? We mentioned zero trust architecture earlier. Could that help?
Yes, zero trust architecture, or ZTA, is a really different way of thinking about security. The core idea is simple but powerful. Never trust, always verify.
Okay, so instead of assuming things inside the network are safe.
Right. ZTA assumes nothing is inherently safe. It recognizes that with cloud, remote work, all these connections, the old idea of a secure inside versus a dangerous outside network doesn't really hold up anymore. The NIST guide really breaks down ZTA principles.
So what does never trust, always verify mean in practice?
It means you constantly check everything. Every user, every device, every application trying to access any resource needs to prove its identity and its security status every single time. Doesn't matter if it's inside or outside.
Okay, that sounds much stricter. What are the main principles?
Well, NIST outlines several. Explicit verification is key. Always verify identity. Least privilege access, only give the absolute minimum permissions needed for a task. Microsegmentation, break the network into small isolated zones to limit damage if one part is breached.
So a breach in one area doesn't spread easily.
Exactly. Also, data-centric security focus on protecting the data itself with encryption and access controls, not just the network. And continuous monitoring, constantly watching the security health of everything in the system.
That does sound more granular, more proactive. How does it actually work? What are the bits and pieces that make up a ZTA?
The NIST doc describes the logical components. You've got a policy decision point, or PDP, that's the brain making the access decision.
Allow or deny.
Right. Then there's the policy enforcement point, or P, that's the gatekeeper actually enforcing the decision, blocking or allowing access to the resource. The PDP itself has two parts. The policy engine, which does the evaluation based on policies and real-time data, and the policy administrator, which manages those security policies. These are separate from the actual data flow.
And what kind of data does the policy engine look at?
All sorts. User identity, device health, location, time of day, threat intelligence feeds. Plus, you need strong identity management systems, security monitoring tools like SUM, and these continuous diagnostics and mitigation CDM systems that keep tabs on asset security. Figure 2 in the NIST doc shows how they all fit together.
And can you set up zero trust in different ways? It probably isn't one size fits all.
Definitely not. NIST describes different models. You could have agents on each device talking to a gateway, or protect specific enclaves of resources, maybe for older systems, or have users go through a secure central portal, or even run applications in sandboxes on the device itself. Figures 3, 4, and 5 show these options.
They also mentioned a trust algorithm. What's that?
The trust algorithm is what the policy engine uses to make its decision. It takes all that input, user identity, device security, context, threats, and calculates whether access should be granted.
How does it calculate?
It could be simple rules, or it might assign risk scores to different factors and come up with an overall trust level. Maybe it's just allow deny, or maybe it adjusts the level of access based on the calculated trust score. And importantly, it can learn from past behavior too, making it adaptive.
Okay, zero trust sounds like a really robust approach, maybe well suited for these complex AI systems. But does ZTA itself have weaknesses? Can it be attacked?
Good question.
Yeah.
ZTA isn't foolproof. NIST points out potential issues.
Yeah.
For example, denial of service attacks aimed at those core components, the policy engine or enforcement point, could potentially shut down access for everyone.
Right. If the decision maker is down, no one gets in.
Exactly. And there's always the risk of compromised accounts or insider threats, someone with legitimate access abusing it. That's why those continuous diagnostics and mitigation systems are so vital. They're constantly scanning for weird behavior or signs of compromise within the ZTA itself.
So even with zero trust, you still need that constant monitoring. Okay, let's circle back to the AI agents themselves and when they fail. That ArcSafe paper analyzing failures in multi-agent LLM systems, what were the main takeaways there?
Yeah, that paper gives a really sobering practical look. They tested popular multi-agent frameworks and found 14 distinct ways they can fail, which they grouped into 3 main buckets.
What's the first bucket?
First is specification and system design failures. This is where the system just doesn't follow the initial instructions or design properly, like that chess game example, not using the right notation.
Right, misunderstanding the spec.
Or agents not sticking to their assigned roles, or getting stuck repeating things, or forgetting the conversation history. They give another example of a phone agent needing a phone number to proceed, but kept trying to use an email address, even though the documentation said it needed a phone number. Just failed to follow the process.
So fundamental errors in following the plan or the rules, that covers quite a bit. What were the other failure categories?
The second big one was inter-agent misalignment. This is all about breakdowns in communication or coordination between the agents.
Okay, teamwork failures.
Exactly, like agents not asking for clarification when things are fuzzy, or the whole task getting derailed because they aren't on the same page. Or, and this is interesting, agents withholding important information from each other.
Withholding information, why would they do that?
The paper gives a scenario where a subordinate agent knew something was wrong with the supervisor's instruction, but just didn't speak up, leading to a failure that could have been easily avoided if it had shared the info.
Wow, okay. And the third category?
That was task verification and termination failures. Basically, problems with checking the work and knowing when the job is actually done.
So not finishing properly or checking the results correctly.
Right. Things like stopping the task too early,
Hmm.
or doing incomplete verification, or just doing the verification completely wrong.
Got an example.
Yeah, the verifier agent for a software project that only checked if the code compiled but didn't actually run it to see if it worked correctly, like checking if the chess game followed the rules of chess.
Ah, okay. A very superficial check.
Exactly. Another one was a math problem about buying fish. The agent mixed up the number of fish with the total cost. A really basic verification error.
Hmm.
They even saw a system solve one math problem correctly and then just start answering a totally different, unrelated math problem in
Hmm.
instances where agents just ignored correct input from other agents.
So lots of ways for the checking and finishing steps to go wrong too.
Definitely. And the researchers stress that fixing these often isn't easy. It's not just simple tweaks. It might require fundamental changes to how the agents reason and communicate.
This really brings us back to the start, doesn't it? Trust. If agents can misunderstand us, fail to work together, make basic verification errors, it really makes you hesitate before relying on them for anything important.
It absolutely does. The potential is huge, but these findings really drive home the need for incredibly careful design, exhaustive testing, and strong security.
Mm.
Hopefully you get a clearer sense now of just how complex it is to build AI agent systems we can actually truly rely on.
So, thinking about all these risks, the security holes, the failure modes, what are some potential ways forward? How can we make these systems more trustworthy?
Well, several ideas are floating around. One big one, tying back to zero trust, is the principle of least power or least privilege.
Okay, give the agent only the absolute minimum access it needs.
Exactly. Don't give an agent access to your email if its job is just to check the weather, limit the potential damage if it does get compromised or goes haywire.
Makes sense. Anything else?
That Hacker News discussion also brought up using techniques like prepared statements from database programming. The idea is to structure interactions, especially security-sensitive ones, so that input data cannot be misinterpreted as an executable command. Prevent those injection-style attacks.
Ah, okay. Building in safeguards against the data is code problem. What about fancier tech? Cryptography.
Yeah, that's where things like zero-knowledge proofs, or ZKPs, come in. One source mentioned these.
Zero knowledge proofs. How do they work?
They're pretty cool, actually. They let you prove something is true without revealing the underlying information that makes it true.
Huh. How's that useful here?
Well, imagine an agent needs to prove its identity to access a service. With a ZKP, it can prove it has the right credentials without actually sending those credentials across the network.
Oh, wow. So it proves identity without risking the secret itself.
Exactly. Or you could use them to verify transactions in a decentralized system without revealing the private details of who sent what to whom. They offer confidentiality and security, which could be really valuable for building trust in these distributed AI networks.
That does sound powerful for verification and privacy. But
Yeah,
going back to zero trust for a sec, NIST did say no single vendor has a complete solution yet. Doesn't that create its own problems, patching things together?
that's a really important practical point, yes. Right now, implementing ZTA often means piecing together products and services from different companies.
Yeah.
And NIST warns this can create a complex web of dependencies. If one part fails or is misconfigured, it could have knock-on effects across many systems, potentially hurting security or just making things unreliable. Building truly robust decentralized systems is still a work in progress.
So it really feels like we've come full circle. We started asking, can AI agents lie? Can they steal our stuff? And we've seen just how complex multi-agent systems are, the potential security traps like tool poisoning, the many ways they can just plain fail, and then these potential fixes like zero trust and ZKPs, which are powerful but still evolving.
Yeah, exactly. Building trust isn't simple. It's
Yep.
not a switch you flip. It requires constant attention to security, privacy, and understanding all the ways things can go wrong.
Right. It's clear that while the potential of AI agents is enormous, getting to a point where we can truly trust them, especially
Yeah.
in these decentralized, interconnected ways, it's going to take a lot more work.
A tremendous amount of work. But hopefully, listeners now have a much better handle on the specific challenges and the kind of thinking needed to build more reliable AI systems.
And maybe it leaves us with a final thought to chew on. Given all this complexity, all these potential failure points and vulnerabilities, how do we even begin to think about accountability? If an autonomous AI agent operating in some decentralized network messes up or causes real harm, who's responsible? How do we build frameworks for that?
That is a huge, critical question for the future, isn't it? Something society really needs to grapple with. as this tech keeps moving forward.
Absolutely. Well, this has been fascinating. We definitely encourage everyone to check out the source materials for more detail.
Yes, definitely worth exploring further. And we hope you'll join us again for our next deep dive into these fast-moving areas.